Hello, in this video, we'll be discussing serial communication with a focus on how it pertains to the Arduino Uno Rev 3. We'll be talking about I2C, SPI, and UART, along with a bit of a brief introduction to some of the other techniques and protocols. So what is serial communication? Well, it's any method of communication between electronic devices where data is transmitted one bit at a time over a channel or wire. Technically, this began all the way back to visual telegraphing systems. Something as simple as somebody on the battlefield waving flags or making gestures to indicate a specific message would be a form of serial communication. When an electric telegraphy arrived, the system had to transmit a single symbol at a time, which of course could be repeated. And this is one of our earliest examples of essentially a binary system, either dots or dashes. Teletype machines took that even further. The machines took over the actual mechanism of transmitting and receiving. It could be a lot faster. Messages could be much more complex. And then all of the stuff with teletypes that moved well through the computer era and really formed the beginning of serial communication between electronic devices. It was generally the earliest and simplest method for communicating between computers and other devices. Teletype machine essentially could send signals to the computer and back. Um, there are many methods, historical and current, and just because they're all serial doesn't mean they're even remotely compatible with each other, at least not immediately. One of the biggest differences between methods is whether it's a synchronous or synchronous. An asynchronous system like UART that uses an agreed upon rate of transmission, but it may use some other techniques to make sure that the messages are being sent and received reliably. A synchronous system may use a separate clock pulse. It may agree on very strict bit transmission rates, or it might be using something like an encoding system within the data stream, such as Manchester encoding. As I just mentioned, serial standards can either synchronize the signal with like a clock pulse, but in that case, you often need a second wire minimally, or you can recover the timing from within the main signal. You have a couple of different options here. For a clock signal, I2C, SPI, shift registers, parallel, internal, synchronous stuff that all use the clock signal. You may use a start-stop bit to resynchronize the signal, known as kind of a UART style. Um, Aspects of the Arduino, RS-232 teletypes use this. You've got transition-based self-clocking, Manchester encoding, classic Ethernet uses this, RFID, some infrared protocols do too. You've got block encoding, usually 8B, 10B, 64B, 66B, PCIe, USB 3, SATA, high speed Ethernet all use this. Then there's oversampling and phase lock loop recovery. Some Ethernet, uh, PHYs uses, some fiber optics, a few other things. And then you have a thing called bit stuffing that's used with USB, CAN. But with the synchronous, there's no short clock. Both sides agree on a baud rate in a frame format. Um, the frame can include like idle state, start bit, data bits, optional parity bits, stop bits. There's ones that are set in frames, but there is unframed, and that's just kind of raw serial data. I don't see it used a lot though, but it can be something you can easily put together. Now, in this video, we're not going to be going into the details of how serial communication works on a lot of other devices. We're going to be focusing on development boards. Well, you start out with UART, that's asynchronous. It has a send and receive line, so it has TX and RX. Lines are switched, so the TX of one device goes to the RX of another device. It's framed with an agreed upon frame format and baud rate. Then we have SPI, that's serial peripheral interface. It's four wires, essentially data in, data out, clock, and chip select. I2C, that's integrated circuit, two wires, one for data, one for the clock. You've got CAN, that's controlled area network. It's mostly for automotive industrial use. your car is basically a computer network on four wheels. It uses two wires, one for high, one for low. The voltage differential is actually what communicates bits in that case. We've got serial, software serial, which is serial emulation. You're just toggling GPIO pins, kind of like pulse width modulation, simulating hardware serial communication and providing a pretty simple UART. You've got a LIN, which is very uncommon in dev boards. It's a single wire system used in automotive subsystems for really simple things like your windshield wipers or whatever. Um, USB wireless interfaces, a lot of things can emulate serial, but the actual protocols behind them is not serial. All right, first we've got UART. This is Universal Asynchronous Receiver Transmitter. Uses a baud rate, which is symbols per second, but for our purposes, it's mostly bits per second. 2600 and 115, 200 are probably the most common. If you're not sure, then use 9600. It has a certain frame format. First, it has an idle line, which is what the line's default state is when it's not transmitting or receiving. It's almost always going to be one or high. I have yet to encounter a situation where it's low, but in theory, it's possible. Then we have the start bit. That's always opposite from the idle. So the start bit is usually going to be zero, low, whatever. Data bits, how many are transmitted at a time? It can range from 5 to 9, but in virtually every case, it's going to be 8. You may never need to change this, but if you got a hold of a really old device from 70s, 80s, possibly, I can only think of one, maybe two instances in my entire life where it's been anything but 8. The parity bit, this is completely optional, but if you want, it can be odd or even. Very basic form of error checking. It's rarely used, so the default is none. You've got stop bits. This can be 1 or 2 bits. The default is 1. I've never seen an instance where it's actually been 2 bits, but it is out there. So 8 in 1 is by far the most common configuration. That's going to be 8 bits, no parity, and 1 stop bit. You might see 7, even 1 for some older systems and devices, but again, this side of the last 30, 40 years, I haven't seen any. In terms of baud, 9600 baud is going to be about 1.04 milliseconds per byte, assuming 104 microseconds per bit, and assuming a full frame of 10 bits. Now I'm going to focus on UART with the Arduino. The Arduino Uno Rev 3, there is one hardware-based UART bus. This splits off both into the serial over USB and a user interface. So you have one hardware-based UART that you can use. Pin 0 or D0 is the receive pin. Pin 1 or D1 is the send pin with an external device. You want to connect the send to the other device's receive and back and forth. This can also function for like two Arduinos, but there's only so many things that simulate this. You can use it for all sorts of things. A lot of modules to connect to Arduino. As I said, other Arduino sensor modules, some industrial devices. Although with industrial devices, you're going to probably be messing with RS242 and level shifting. And there's plenty of variants that might also use something else like I2C, SPI, CAN, etc. Some basic commands, you got to get the connection started. It uses a serial library, which we've already been using for like print and print line and again, the serial monitor. You have to begin. If you want to end, you end. You can flush. You can also check if there's available data on the line, read strings, and a bunch of other things here. Some interesting things like serial peak will read the next value, but it won't. It'll tell you what the next value is, but it doesn't officially read it. It still keeps it ready and available. You can also set timeouts and some other stuff. Always keep in mind the most important thing is baud rate. It's got to match. Some really small data like might not be affected, and that might give you a false positive, but anything more than that, it will show really screwed up, just like random characters. We've also got something known as software-based serial communication, and it basically toggles GPIO pins kind of like pulse width modulation. And you can use it to emulate UART with some pretty decent results. Like it probably can't really go reliably higher than 9600, but still has some pretty precise time controls. It'll generate the bits manually, good timing loops, good CPU usage. It's a great way to actually learn how UART works using serial. Um, you can basically pick pretty much any two GPIO pins to work for your send receive. You still want to avoid its pins 1 and 2 or 0 and 1. Um, it's also a good idea to keep 10, 11, 12, 13, A4, and A5 free because those are I2C and SPI. But if you use them and you're not using the other stuff, it may not be much of a deal. You've got a software serial library. There are some alternatives that address some of the issues with it, like alt-serve serial I've used, Neo SW serial, and then there's like Tiny software serial. But I think that needs USI on an MCU. We're not going to go into that right now. You basically define your pins, you create an object, and you can do whatever you want with the object with, I think, everything coming from all the keywords coming from the object, basically being like the regular serial one. That's the point, actually. All right, so I've made another little custom chip here just to show UART in action. It's connected to the send and receive lines, and obviously send to goes to the receive on the chip. Receive comes send on the chip. It's going to talk back and forth here. So the serial monitor displaying the displaying the actual number. The chip's converting, and there we go. Pretty simple. Keep in mind the baud rate up here too has to be set. So I set both to 115 to 100. All right, I brought up Simu IDE because we can actually simulate multiple things with this. We've got two UNOs, so you've basically got the same program, transmitting, receiving, back and forth. There's two lines. Sending from one goes to receiving the other and vice versa. You kind of get a idea of its transmitting. It's not as obvious on this other line. This is what it looks like from the first one, I believe. So it's sending a message and receiving. I really should have done Arduino 1, 2, whatever, but I was lazy. Then from the other one, we have just the opposite. All right, next we have I2C, or integrated circuit. It's a synchronous serial communication bus designed for multiple devices to communicate with just two signal wires. Now, a bus is a shared communications pathway between multiple devices for the purposes of sharing data. In theory, you can have up to 128 devices on a single I2C bus, but addressing for most devices are fixed, often to a single address or just a handful of options, so the reality is a lot less than 128. They generally use open drain or open collector depending on if they're using BJTs or MOSFETs. So they generally need pull-up resistors pulling both data and clock to VCC. I usually recommend a 4.7 kilo ohms resistor. It should be sufficient. You might want to increase it to 10 for certain light loads. You might want to even decrease it for heavier loads, but start with a 4.7, assuming you have a 4.7. It does have different speeds depending on the mode. Standard mode goes up to 100 kilohertz, fast is 400, fast mode plus is 1 megahertz, and then we have high speed that goes up to 3.4 megahertz. Now, standard and fast modes are usually the ones recommended for Arduinos. Pretty much every device is going to support at least a standard, maybe also fast mode. The other ones are a little bit more touchy. Always check all the data sheets for everything you plan to add to the bus. You basically have to go with the lowest available mode across the devices. If you don't want to do that, just do standard mode. If you're doing something pretty simple, it's not going to really matter. The wire library is the standard for the Arduino, so you'll include that and use stuff from the wire library. But there's other options, especially for software-based I2C, just like we talked about. There's software-based UART. They exist in like tiny wire in, tiny wire S. Those things are really meant for at tiny MCUs, but I think you can use them with other ones. I've never have. Software wire, same idea. You can use it to create a second software-based I2C on pins 2 and 3, but the speed is best well below standard mode, and there's some other limitations and issue, but in a pinch it could work. Okay, let's take a look at how I2C works on Walkly. Now, there's two big limitations. One, the microcontroller dev board that you have out, you can only have out one, and it can only be the controller as far as I know. Now, I've made a silly little example here of a custom chip in Walkly. Actually, I'm not so silly, I'm actually kind of proud of it, but basically it lets you set the color as RGBA, so red, green, blue, and the alpha channel. So we're including the wire library here at the top. We begin transmission. I'm not even sure why that's in there. Oh, it doesn't like that. What is it one actually? Transmission, does it want a baud rate? No, that's not make sense. It's I2C. Um, the you know what? I'll just put what was ever there because it doesn't matter. Oh, maybe you just need something in there just to acknowledge that it's gotten a signal. Oh, okay, let's see what happens if we do. Okay, that doesn't cough up anything. Oh, actually, anyway, so yeah, maybe it did actually need the 22. It's weird. Okay, there we go. So it needed a signal. I'm not even entirely sure. Would no. Okay. Anyways. Oh, just realized it's actually its address. All right. Okay. So we begin transmission to this device by that address, and we're gonna write, and we're using wire write. We can send it a byte at the time, and then we're gonna end transmission. So in this case, I've got it set up so that it reads in 4 bytes: red, green, blue, alpha. And if you want to see how this actually changes, this should be there's green to let's just put a little bit of red in there. Changed it. Now I can make this a little bit bigger to see if we want. Let's take out the red. Let's put in some blue. And this is the alpha channel at the bottom. So yeah, we get kind of a off-white color. The color isn't exact. That technically should be white right there. Change, take out the blue aspect. Go. Got red and green, mix yellow. Red and blue should make purple. Yeah, there we go. So, yeah, pretty simple. We've got our SDA lines. Now, I've had it connected up here at these 2 pins that are above AREF. It does work in Walkway. Otherwise, it would be 4 and 5 down here. So, yeah, this would be 5. Mind you, these pins are connected to those down there. So, um, we've got data on 5. We've got clock 4. So those are the pins to use for the Uno. All right, now here's a complicated I2C bus that I set up. just to show off a bus, I've got one, two, three, four, five devices. Well, technically, the Arduino, we got six devices connected, and it's going to do a scanner. I've listed what the addresses of everything are. Now, since the Arduino is the controller, I don't have to worry about an address for it, but everything else is a peripheral. So at 2.7, we've got this LCD. At 3C, we've got this little OLED monitor down here. At 68, we've got this, I think it's humidity. Oh, acceleration gyro sensor. All right, and then we've got PU at 69. Chip, no, the chip's at 22. Oh, they just have things labeled correctly. 1, 2, 3, 4, 5, 6, 5. Oh, maybe we don't have a sixth device hooked up. Weird. Anyway, so I have the wire library. Now we're also using something from SPI, I believe. I think we actually have to use that for something in here, maybe. Not really sure. Maybe the display. We also have to use the libraries for everything else. Our liquid crystal, our graphics, our SD is all in here. So we're setting up a bunch of different devices. Ignore all of this. We're setting up our serial because we're going to use this as a scanner. We have to set things for the LCD, and then we're looping. We're checking devices. We're doing begin transmit at every address possible, and then error in transmission because in transmission is going to give us some kind of error with most devices. Um, if it finds something, it will send it. I'm having it send to both displays, and then the other stuff is just for the devices. But let's see what happens. Okay, we got the scanners scanning. On our first 27, 22, 27, 3C, 68, 69, and we're done. And then this is the wiring here. We've got ground, and then no, okay, we do got power. We got them switched across. But yeah, everything is pretty much going to be, I mean, two wires for signal, and then power and ground for everything else. Then we have SPI, or Serial Peripheral Interface. For literal years, I was calling it Small Peripheral Interface. It's kind of like the big brother to I2C. It's synchronous, full duplex, although there are half duplex options. Controller peripheral communications protocol, where a controller device controls the clock, selects which peripheral it wants to talk to. We've got full duplex, where it can do both at the same time, half duplex, where it can only do one or the other. It uses four signal lines, and the naming of this, there's a controversy behind this, but clock SCK is usually clock, although it might say CLK or something. We've got what's traditionally called MOSI, which is master in, master out, slave in. I like to call it COPI. That's new terminology standard. So controller out, peripheral in. You've got MISO, which is master in, slave out. Again, I prefer controller in, peripheral out, and SS, which is slave select. I prefer the term chip select, or CS. Just keep in mind the two different naming conventions and the controversies between the two. Standard SPI on the Arduino Uno Rev 3 is D11, 12, 13, and 10. But technically, I think you can actually use other pins for the chip select. I've never done it, but if not mistaken, it's possible. The standard library is the SPI library, but there's also a software-based SPI that you can do. It has four modes, and everything kind of has to support whatever mode. Basically, it affects clock pro. It affects clock polarity and phasing. So there's mode 0, 1, 2, and 3. Most devices are going to use mode 0 or 3. Some devices can do more. Pretty much, I think every device has to support at least mode 0, but I'm not entirely sure about that. Speed can either be 4 megahertz or 8 megahertz, so it's a lot faster than I2C. So usually devices that have actually got to communicate some significant amount of data are going to use SPI, but there are devices that use either or. There's no need for addressing in this case, um, but you have to use chip select if it's present. If you've got an SPI connection that's not using a chip select, then you're pretty much just limited to a controller and a peripheral. The thing is, this is all more complex since it requires more pins. The more devices you have, the more complicated you get, and then suddenly your bus is just utterly crowded. So let's take a look at our first SPI bit. This is an SD card reader. You can get these a dime a dozen. Keep in mind there can be, it's not going to read quite as fast, but you'd be surprised what you can do with this. Essentially, you can add yourself a hard drive to an Arduino pretty easily, and what it can handle in terms of size and speed, that's going to depend the specific reader. I wouldn't use it to stream. There's definitely, this is on the lower end of things definitely. Um, but yeah, we've got data out, which would be MOSI or COPI 12. We've got our ground. We've got our clock 13. We've got our power. We've got our data in, which be MISO or CPU uh, here on 11, and then we got our chip select um, on 10, should otherwise be SS. That doesn't make it any less problematic, I suppose. Problematic in two ways, but anyway, so we've got our 4 data lines, we've got our power, we've got our ground, we've got our SD card reader, and we have SPI library, but we also need a library for the device, so we got SD. Let's see, we set the chip select line because technically the chip select line we could use technically anything, if I'm not mistaken. I mean, you don't generally want to use 0 and 1, but yeah, you could set it anything but 10. 10 is just kind of the default. Right here, it's waiting for the serial port to actually connect. Um, and then it's going to initialize. It's going to initialize the card, which is not part of the SPI. Going to give us a bunch of information here. So, but the SPI side of things is the more mixed in here. Let's see, SD card library is doing everything. I can't remember. It's been a while since I touched this. But all right, let's run it and see what happens. All right. Well, it's telling us what kind of cards, an STHC. It's telling us clusters, how many blocks in a cluster, telling us our file type, sizes there. So it's what? 7.8 megs, I guess. 7 point whatever. And then the files that it finds on here. And in this case, we got an SD card. It's listing the stuff that's here. So the diagram, it's listing these 3 files as part of the SD card. If you have, I think one of the paid plans, I think this is true for anything, you can actually upload files. Do this in a couple of different ways. Here's another SPI example. Little graphics test of ILI 9341. It's got a lot of pins. Keep in mind, we got power, we got ground, we got chip select. There's no reset functionality as far as I know with this. Um, let's see, it's DC again. Not remember off the top of my head. But we got the MOSI or the COPI line. We've got the clock. We've got an LED that either doesn't work or it's simply not connected. We've got our MISO CPO lines. So we've got all the basics here. Let's turn it on. Just going to display colors. Obviously, this would look a lot better in real life. All right, so we've got our SPI library and some other stuff too. So let's go through here. So it's just assuming, there's nothing too much to set up with the SPI. We're really just beginning, and we're specifying some DC and CS lines here. Just going through. And then all of this is pretty much for the graphics in the screen. Then we have CAN or controller area network or controlling area network, depending on who you ask. It's designed for automotive and industrial applications. Um, one of its big benefit is that it has high resistance to the noise that's generated by machinery. And by that I mean electrical noise. Your car uses this. This is what keeps your car all synced up. Yes, your car is a computer network, and it's probably been that way since sometime in the 80s. A message is basically broadcast across the network. Individual devices decide what to do with that message, if anything. Um, so it uses voltage differentials instead of the actual voltage levels. You've got a high line and a low line, and the difference between the two determines the zeros and the ones. Again, this is because using voltage levels can be very disruptive by the electrical noise in a vehicle. Classic CAN, that goes up to about 1 megabits per second. FD is like 5 or 8. It can be larger. The Rev 3 doesn't have native support, but you can interface with like CAN interface controller through SPI. Um, you can use it to connect to your automobiles diagnostic systems like OBD2. So yes, you can use a dev board to essentially do stuff with your vehicle. People have used them to make special custom dashboards for diagnostics to give you more information than your typical dashboard does. You can even change some things in the computer, um, values for things like fuel ejection. Keep in mind, if you do this, you probably void your warranty. It's also good for robotics, distributed systems. There are a bunch of dev boards, and they're doing a line that do have native CAN support built in. Um, but even without native, it's not that hard to set up with an SPI interface. The Rev 4 has support, and there's an Arduino underscore CAN library. If you did it with a Rev 3, you would need both the SPI stuff and specific um, libraries for that specific interface device. And then we have LIN, or Local Interconnect Network. This is a little bit older than CAN, but it works in concert with it in a vehicle. It's simpler and cheaper protocol, but it handles simpler things like, say, the vents on the motors on your AC vents, or maybe your wiper blades and how that works. Again, it's just very simple for very small and simple things. Just uses a single data wire or ground wire. It uses a pretty simple single controller slash master and then multiple peripheral slave with time triggered communication. A message starts with a header issued by the controller, includes a break signal, sync by identifier. The peripheral that it is sending that message to responds to with 1 to 8 bytes of data and a checksum. It's not supported by any of the Arduino boards, but you can easily get a UART interface to LIN transceiver chip. STEM32 boards is where this really is great because it has a lot of support for CAN and LIN, but you still need a transceiver all the same. Now let's wrap things up. Well, serial communication is 1 bit at a time. over a channel or a wire. We talked about synchronous and asynchronous. We also talked about how asynchronous can be framed, who it usually is, or you've got unframed, where it's just raw serial data. You've got clock signals, stop bits, transition based, self clocking, block encoding, oversampling in PLL, and even bit stuffing. We didn't talk about most of that, but future videos we may. UART, SPI, I2C, CAN, and LIN, we all talked about those in depth. We talked about serial emulation, like serial or USB, and the software serial libraries. UART is just two main wires, send and receive, and pins 0 and 1 on the Rev3, but you can only interface with one device. I2C is two signals, data and clock. There's different speed modes. In theory, you can have 128 devices on a bus. In practice, it'll be a lot less. Each device needs a unique address, though. SPI, we've got four signals, clock, the controller in, peripheral out, the controller out, peripheral in, and the chip select. It's much faster than I2C, but it's much more complicated. More devices are going to need more wires connecting to the bus. It also has four different modes based on clock polarity and phase. And we talked about CAN, that's two wires used for linking automotive system. It works off a voltage differential, so that it can resist all the electrical noise that's coming off the motors and whatnot near it. We talked about LIN, that's just one wire plus a ground. It's used for simpler automotive systems. Usually it's used also with CAN, so LIN handles the simpler stuff in a vehicle, CAN handles everything rest. Well, until next time, have a good one.